Okay, thank you. So I'm going to be talking about surface temperatures, mainly focusing on a model we're developing to aid in our interpretation of diviner observations. For those of you that caught Ben Greenhagen's talk yesterday, he already talked a bit about this, but the lunar surface exhibits extreme spatial variations in temperature, just due to the fact that it doesn't have a substantial atmosphere to buffer surface temperatures. And so very large, very strong thermal gradients can be maintained throughout the daytime, all the way down to the diurnal skin depth length scale of tens of centimeters. And so, there can be a very complex scene of temperatures beneath the spacecraft within a single surface footprint of the instrument, which complicates interpretation of temperature measurements. So what we're doing is basically developing a three-dimensional heat flow model, looking at heat flow in the upper part of the regolith to try and understand how various factors will influence what diviner observes. So we're looking at heterogeneous thermophysical properties and also how topography with slopes and shadowing can affect what we see. And so there's a ray tracing component to our model as well. So just a quick overview. Diviner is mapping the thermal state of the moon, measuring both reflected solar and emitted infrared in nine spectral channels. And so the main goals are to characterize the thermal environment of the moon, look at surface properties such as thermal inertia, rock abundance, silicate mineralogy, and then also look at locations where volatiles might be cold trapped and be stable. So this gives us the opportunity to really look at the energy balance, surface energy balance of the moon, and try to understand how the regolith stores and exchanges heat. So here's an example of one of the maps I put together. This is daytime volumetric temperatures of the South Polar region. And since we're looking at low sun angles here, you can see that topography really creates quite a diversity of temperatures. And just due to the shadowing and slope effects of the topography, and these shadows, are really maintained at all length scales, all the way down to very small scales. And so the question then is, what does that mean for a temperature measurement by diviner, where you have a very complex temperature field beneath your instrument, and you're really just measuring some sort of integrated effect of all these temperatures. So to kind of give you a sense of the diviner footprint scale, the instantaneous field of view at about 50 kilometers, which is sort of the average altitude, you're getting about 250 meter footprint size. In practice, the footprint size is actually quite a bit bigger than this, and I'll come back to that in a little bit. But the idea here is to just model the upper part of the regolith, and model heat flow, and try to account for some of these factors that will influence surface temperatures, and try to understand them a little bit better. So we're looking at topography. We look at vertical variation and thermophysical properties, and then also lateral variation. So, for example, looking at rocks embedded in the regolith and how that's going to affect surface temperatures as well. So we basically have a three-dimensional model. We balance insolation with emitted infrared and conducted heat into the subsurface, and basically try to see how varying all these various parameters affect the ultimate volumetric temperature that diviner might measure. So in the nominal sort of regolith model here, we're adapting thermophysical properties selected to match Apollo heat flow experiments, and we're using values from Siegler et al. 2011. So our nominal sort of regolith here, we've got a very low density. So we've got this low density, fluffy, low thermal conductivity layer beneath which there's a more competent layer that increases in density very rapidly with depth. And then we have temperature dependent conductivity and heat capacity. So in a one-dimensional model, given sort of a two-day insolation cycle, you get sort of, these are superposed thermal profiles now in the regolith. So this is showing the diurnal heat wave penetrating into the regolith, and then you can see the inflection due to that interface with that low density fluffy layer on top, which acts to exaggerate the amplitude of the maximum and minimum temperatures. So the idea then is to expand this into 3 dimensions now and start looking at lateral variations in thermophysical properties. And this is also fairly similar to the modeling that Ashram and Vasavid et al. Did as well, where they also did a 2-layer model. For those familiar with his work. So here's an example now in 3 dimensions where we've embedded a rock of 2 different sizes. So this is a hemispherical rock that's just flush with the surface. So we have no topography in this particular run here. And you can make out the low density layer at top. It's got a low thermal inertia, so it responds very rapidly to changes in illumination conditions, whereas the rock that's in the middle of the scene with a higher thermal inertia responds at a much more, it lags behind the surrounding regolith in its response to illumination conditions. So having an embedded rock in the regolith really largely is going to affect the nighttime temperatures, since the moon lacks a substantial atmosphere. The sensible heat stored in the daytime in the subsurface is the only heat available to balance the loss of emitted thermal radiation into space during the long lunar night. And so rocks can store more heat. They provide a reservoir for heat. So the larger the rock, the larger that reservoir. And so the surface temperatures that are observed for regolith with rocks will be warmer throughout the lunar night than a rock-free regolith. And those temperatures can be actually quite a bit different. And you can actually see that a little better here. So now I'm plotting the blue curves are the diurnal curve of the surface temperature of regolith with no rocks, and then the red curves are then the surface temperature at the center of these rocks for the 7 centimeter diameter rock and the 14. And so you can see at the daytime, as the temperatures go up, the temperatures don't vary that much, but in the nighttime they actually diverge quite a bit. And as you go to larger rock sizes, the difference in temperature gets larger. So I wanted to take that a bit further and sort of look at different ratios of rocks and regolith to see how that would affect brightness temperatures observed for the diviner instrument. So what I did was sort of work out what the effective field of view of diviner actually is, because it's not the same as the instantaneous field of view, and that's partly due to the fact that you've, just because the spacecraft is moving, you've got some finite integration time, so you get some smearing in the in-track direction. So what I'm showing here is the instantaneous field of view is the black, but then you've got some integration smearing in the long track, and then you've also got the sensor has a slight amount of memory of what it just saw previously. So you get this, it's called sensor response time broadening, that if you take that into effect and you sort of convolve all these together, you get some probability distribution of what you're actually seeing in the in-track. So I use this to create basically a 2-dimensional probability distribution of what diviner is actually seeing on the surface and what its actual footprint is, and then just basically doing a Monte Carlo sim. And, so here I just took 5,000 points and used this distribution function, and then just unbinning. This is just a normalized histogram, and so really this would be a box that's about a kilometer by 1 kilometer, and so this gives you a better idea of what the actual footprint of diviner actually is on the surface. And so then I just took different ratios of rock and regolith and just put it within beneath the diviner instrument and just took some average, basically determined what the bolometric brightness temperature of diviner would be for that given scene to see how it is influenced by different rock sizes and different ratios of rock to rock-free regolith. And so here's the results for, again, a 7 centimeter and 14 centimeter diameter rock. So you can just kind of get an idea of how the rocks affect nighttime temperatures. So this would be the temperature difference relative to a completely rock-free regolith, and then different surface area fractions that are filled with rock. And you can see as you go to and then each symbol represents a different time throughout the night, so going from early evening down to dawn. So the rocks are cooling, but you can see that the bigger rock is just a lot warmer. It stays warmer throughout the entire night. So it's not only rock fraction that's important, but also the size of the rocks actually is quite important as well. So then the next step is in the model we added in topography and ray tracing, so we now start to capture shading and slope effects. And again, you can see the rock stays warmer during the night. So here we're using a spherical rock now that's halfway out of the surface. And so now you can see the daytime temperatures will be affected as well. And of course, now the viewing geometry actually becomes important as well. So now you can imagine if your viewing geometry is similar to your illumination geometry, then you're going to be largely seeing slopes that are sloped towards the sun and are going to be hotter relative to if you're now at a large phase angle where you're predominantly seeing slopes now that are tilted away from your illumination angle, and you start to see shadowing. So your average temperatures of the scene will also vary as well. Okay, I'm actually a little ahead of schedule. So what we're trying to do here is really try to understand how these very extreme variations within temperature at scales much smaller than the diviner footprint actually translate into a measured single measurement of temperature. So we're looking at some integration of a lot of temperatures, and those surface temperatures are going to be very sensitive to the thermophysical properties of the regolith, especially within the top meter where heat flow is really dominated by solar forcing. And so we're trying to, obviously this is a work in progress, so we're really just kind of getting started with this, but the idea is to start to get more quantitative about all the different factors that can influence our measurements and explore different length scales of topography and heterogeneities in the regolith, and try to really determine diviner sensitivity to things like surface roughness and different length scales of rocks. And so hopefully we can start to learn more about the thermophysical properties of the regolith.